So today we will start from the point where we left last working day, means on Friday. So the idea today is the completely like practice session where we will learn that how we can determine the magnetic structure. So today I will start this compound where I left last time. So let me show you this PCR file of this compound. So this is the PCR file, and this PCR file is for room temperature. And let me write down this formula unit or of this. So this compound is NDFeMnO3. This is 0.5, this is 0.5. So this is the formula of this compound. Sorry, I think it has taken some automatic format. So NDFe 0.5 Mn 0.5 O3. So now for this space group, this multiplicity of the site where neodymium goes is 4, and for this side where this iron and manganese goes also 4. Oxygen has two sides, oxygen 1 and oxygen 2. For the one side where oxygen goes, multiplicity is 4, and for the another side where oxygen goes, multiplicity is 8, and the multiplicity of the general site is 8. So now to get this occupancy correct, if site is fully occupied, we have to divide this occupancy of that site by this general occupancy. And let's see how it looks like. So this is neodymium, iron, manganese, O1, O2. So as you can see here that the occupancy for this neodymium is 0.5 because multiplicity of the site where neodymium goes is 4 and general site multiplicity is 8 for this space group. Similarly, in this material, this iron and manganese, so both of these ions goes to the same site and the multiplicity of that site is 4. So the total, if I take this summation of the occupancy of iron and manganese, it should be 0.5 and it is half. So this occupancy for iron and manganese becomes 0.25 and 0.25. Oxygen, I told you, there are two sides. For one side, the occupancy is, the multiplicity is 4, and other side of the oxygen, which is, I believe, this, is general side. So the multiplicity of this side of O2 is 8, and general site multiplicity is also 8. So the occupancy for this site becomes 1. So this is how we have the occupancy. Now if I multiply this occupancy by the 2, then I reach the formula unit. So this neodymium, if I multiply this occupancy, if I multiply by half, it becomes neodymium 1. Iron, if I multiply by 2, sorry, neodymium if I multiply by 2, it becomes 1. Iron, if I multiply by 2, it becomes 0.5. And similarly, manganese, if I multiply by 2, it becomes 0.5. Oxygen 1 becomes 1. And oxygen 2, if I multiply by 2, it becomes 2. So then the formula unit translates to ND Fe 0.5 Mn 0.5 O3. Now I have told you the meaning of this parameters, and in the last lecture I show you a crib sheet. So maybe you can go through this crib sheet and try to keep in your memory some of the short codes which is mentioned in this PCR file. Now, if I have to determine the magnetic structure, then as you know, I have to do the experiment at low temperature. So this is the data at room temperature. Now first, let us have a look at the data of this material. So I am showing only the data of limited range to avoid the to make it easy for you to get it. So this is at 90K. So you can see clearly at 90K, we have some peak enhancement in the intensity. And last time in the last lecture, we determined this magnetic structure. And you can see these positions are the same as like a back reflection of your nuclear peak. So I can open here another tab and try to plot here this PRF file of this 300K. So let me reset it, PRF 300K. So the 5K is by mistake here. Let me correct this. This is comment due to comment. Okay. So this is the data at 300K, and let me quickly run it. Okay, so this is the refinement at 300K. Now you see this blue lines or blue curve here is the data at 90K. So it is clear that we have the additional magnetic scattering at 90K, and now idea is to determine the magnetic structure. So first of all, you can see this peak where we have enhancement in the intensity. They are at the same location where we have this nuclear back peaks. So you can see it here, the first reflection comes around something like 14.1, and you can see here if I zoom it, yes. So this is the position, this is nuclear allowed reflections 14.2578. Second, we have minor increase in the intensity here, and these are also nuclear allowed reflection. One can easily then say that the propagation vector for the ordering is 0, 0, 0. Now our idea is, we know the two things. We know that we have some additional magnetic scattering, and we know the propagation vector for the magnetic phase or for the magnetic structure which we plan to determine is 0, 0, 0. Now the idea is to do this representation analysis and try to find out the magnetic structure. And you know, this magnetic moment, as I defined in the last lecture, is given by magnetic moment M is given by sum over K Skj exponential 2 iota, sorry, iota q dot r. So this is the expression of our magnetic moment, and what we have to determine is this, we have to determine this Fourier coefficient. And this Fourier coefficient can be written as summation of this basis vector So then these are this coefficient and these are this basis vectors. So this basis vector tells us that what can be direction of the moment. So our idea now is to determine this basis vector and then try to see that with this ordering vector 0, 0, 0, what kind of magnetic structure we have and the neutron diffraction data which we are having out of many representation which comes from this k equal to 0, 0, 0, which representation satisfy our neutron diffraction data. So then what we do is we know our ordering vector. We go to this, we close this tab right now. So I go to the program which is base irreps. And here let me open a file. I will explain you. So now here, this is the code, this is the working directory, this is some title which you want to keep it. This is the space group. This is the space group of your nuclear phase, means your phase where you have done the refinement without including any magnetic phase, means paramagnetic phase. This is the k vector which we have determined. So this k vector is 0, 0, 0 and this k vector is gamma point. So we label it as Brillouin zone label as G gamma. Magnetic moment is axial vector. I have put it as axial vector. And number of atoms in this case, magnetic atoms. Of course, we have the two magnetic atoms, iron and manganese, but they are going at the same side. So when we do the neutron diffraction experiment, what we are going to get is we are going to get side averaged moment. And that is why I have written only one atom and I click it here, this atom is in the unit cell. And let me save this file and let me again open it so that to make it sure, let me put the title magnetic phase and let me again save it. It's better always to open it again. So this file generally which is opened by this base refs, it has an extension as MB. So as you can see here, this is the file which is opened by this GUI interface of base refs. You can read this file by this text editor also. Let us see. So if you want to run this base refs by this GUI interface, you can run that also. So this file first is title, short output I have said, I can set this long output also. Space group is PBNA, K vector is 0, 0, 0 and this I have, this is gamma point and this is our atom, axial is the moment and half 0, 0. And now let me close this and I go here. File open. Now let's ask it to run it. It does this symmetry analysis and it produces a file. I will advise each of you to at least go through this file and try to understand the meaning of this different things which are mentioned in this file. Of course, it is a long file, but I think once you should go through this. So now once I run this file by base refs, it is going to generate two files. So I can go in the result. So one is the BSR files and other is the FP file. So in the FP file, this program does a lot of job for you. So it tells you if you want to put or if you want to make your PCR file with this basis vectors. So these are the basis vectors now. So it writes this basis function of representation number 1 of dimension 1 contained 3 times in gamma. So these are 3 basis vectors. This program has given this basis vectors for you. Only what you have to do is you have to copy and paste in a PCR file which is compatible with taking with this moment value, taking with this notation in the terms of basis vectors. So what we do is now, I show you. So what generally we do in this case is we go to the, so let me close this and I keep this file open, which is generated as a FP file, the notepad. Okay. Now I can close this file. Now what we do after this is, let me close this. So we have done this representation analysis. Now we would like to see this magnetic structure corresponding to this symmetry operation. So what we do in the PCR is then, so let me show you. So I go to this PCR. Here I have already added a magnetic phase. But how it is done is that, so if you see your nuclear phase file, so nuclear phase file generally have content, all content other than this highlighted one. So in the last line where it comes here, I have inserted this phase and I have to put here number of phases too. Then what are the different symbols here telling me is that this IRF equal to -1 is telling me that only satellite reflections for the magnetic contribution. Let me note it down. So what is the meaning of this different symbol in the magnetic phase? So we have magnetic phase. So IRF equal to -1 means only satellite reflection for the magnetic contribution. For magnetic and there are a couple of more important things here. ISY equal to -2 tells me that in this PCR file, I will be giving the information about the moments in terms of the basis vector. So ISY equal to -2, it means component of magnetic moment in terms of basis vectors. So this is what I'm telling if I'm putting ISY equal to -2. Instead of this, like what we did in the last example, we used ISY equal to -1. So if I use I it means I will give this information about this moment in terms of this symmetry operation. Like I will write something like magnetic symmetry and something I will write it. So I will not give this basis vector, but I will give this symmetric instructions in the PCR file. And there is one more piece of important thing here in this PCR file is NVK. So this NVK is telling us this number of propagation vector here. And what we have is only one propagation vector, which is 0, 0, 0. And then this information, this when you run this Basireps code, it comes from this Basireps program. So let me show you. So this is the output of our symmetry operation. So iron and manganese goes to the same site, and we have the 4 position in our space group of these sites. Now, this is the block of the PCR file, which directly I can copy it and I can directly paste it here. Now what it is telling is that we have 4 symmetry operation 1, 2, 3, 4. This is the information about the Lovey class, and n base 3 is telling me that I have 3 basis vectors. So it means I will need here at least 3 coefficient for this magnetic structure. And magnetic moment will be given by this. So like for this site XYZ, magnetic moment will be, let me write down explicitly. So the basis vector is 1, 0, 0, 0, 1, 0 and 0, 0, 1. So magnetic moment in general condition can be written as the Fourier coefficient of the magnetic moment, and they are directly moment in this case because k equal to 0, 0, 0. So this will be like C1, 1, 0, 0, C2, 0, 1, 0 plus C3, 0, 0, 1. So this will be our moment. So our idea is to determine this C1, C2 and C3. So we want to get this information about this 3 coefficient to determine the magnetic structure of this compound. So let's go to the full Prof now, and let me close it and let me show it to you how it looks like in the editor. I say save, and I say to this that this was the file I was working at 90K, and I go to edit PCR. So those who are using it first time, they can use this edit PCR, and if you can open this file in this edit PCR, it means your file is more or less correct. Otherwise, this edit PCR will give you some error. Now, I will directly like to go to this pattern. We have only one pattern, and what we have is 2 phases. One is this structural model and other is the magnetic phase. And you can enter here in the magnetic phase that this is with the constant wavelength, and we have to go importantly in the symmetry. So you can see here that I have put I as y equal to -2, means due to which it is coming that basis function of the irreducible representation of the propagation vector group. So what I will be giving here is I will be giving the information about the basis vectors. And these are the basis vectors. So this is imaginary part, real part, and this basis vector has 3 components, and these 3 components are along the direction of your crystallographic unit cell in the real space. So So C1 of this plus C2 of this plus C3 of this we plan to determine. And these are the coefficient which is written here. Okay, let me save it and see it whether. Now a very quick way to do it is like this. You have added this additional phase. This information you are getting directly from the PCR. And the other information which is here is the number of atoms. So we have only one atom, which is manganese or iron. Let me put it as Mn1, and this I put it as. So this code word M is telling me that this atom is magnetic. So I write Mn, and 3 means Mn3 plus. And this half 0, 0 is the position which is given here. And this side, when we write in the magnetic phase, it is fully occupied. Now, this parameters UVW in the starting, you can keep it as same as is there in the nuclear phase. ABC also you can keep it same. Preferred orientation, preferred 2. And this all for asymmetry parameter, you can keep it 1, 0, 0, 0, 0, 0. If you are dealing it here with NOR equal to 1. This is the information about your propagation vector, and we have only one propagation vector. And this this is the range by which you will see the refinement while running this PCR file. Now, what generally looks better way to me is that I make it this number of refined parameter 0, and I just try to see it what kind of magnetic intensity I get it by playing with this parameter. So let me put some parameter like 1, which looks like reasonable value of the moment for the C1, and let me just try to run it. You see it, if I can see it from here, that if I put even a small moment of 1, it tries to generate the intensity at this location where we have no magnetic intensity. So it means this configuration is not good for the magnetic structure. And now if you have only C1 coefficient, it means what it is telling it that if I am writing only C1 equal to 1 and C2 and C3 0, it is telling me by looking at this basis vectors that my moment is aligned along only crystallographic A axis. If you want to see the detail corresponding to this, then what one can do is one can close this, go in this studio, and where we are here in the T90 basis 1. Closed, no, file open. So once I have tried to run it, it generates this two file. One is corresponding to the phase number 1, which is nuclear phase, and other is the corresponding to the magnetic phase. So let me see. So with this representation, if my material ordered, then as you can see, this is telling me that the direction of the moment is along the axis. Right? Let me just try to play it with more. What I can do is quickly to show it to you that I make my C1 coefficient 0 and I can make C2 now 1. Then let me see. I can now let us try to see the magnetic structure. So now you can see the moment is along the B direction. You can see it here. I can also put all this coefficient and try to see whether it helps me somehow You can see it here that still I do not get this good increment with the experimental data. In addition, it gives me this peak where I do not have any intensity. So this peak, if I try to play with this coefficient, if I make this C1 0, let me see how it looks now. So C1 0 I have made it now and I ask it to run. So it means making this coefficient C1 0 is trying to make this intensity here small. So we have the intensity when we have the C1 component at the 0, 0, 1 location. Now, suppose if I make C2 0, how it happens is, looks like voice nahi. If I make C2 0 now,
You can use this one.
so if I make it the coefficient C2 0, let me see how it looks like. C2, C1, C2 0 means I have the only one coefficient which is C3. So as per this basis vectors, now I have only the coefficient associated with this. So my moment is along the C direction. And if I try to run this program, then you see it, this also do not help you in getting this proper intensity. So this is the cycle one has to go through always once you have this kind of representation analysis. And the idea is to see whether you can get this accurate magnetic intensity what you have been seeing in the experiment. And now quickly you can see that what kind of magnetic structure it corresponds. Because you might have some idea of this moment direction from some other experiments. So let me put it here. So as I told you that if I put only C3 component non-zero, C1, C2, 0, with those basis vectors, my magnetic structure will have component where the moment will be along the crystallographic C direction. So this is how we proceed about this magnetic structure. Now you can see it here. If you want to generally quickly see it, generally I put a huge moment and try to see it whether I am having some intensity at the location where this program is generating. So this do not looks to me very favorable condition for the magnetic ordering for this compound. So then what we do is we go to the another representation. So what I do now is, so for going to another representation, I will try to go in the another directory where I have marked it with the basis 2. So let me just open it. So here this nuclear phase is same. What we have to change it now, we have to change this part of this magnetic phase. Now how to do it? Again, as I told you, what we have to go do is we have to go to this FP file which was generated by this BASREPS program. So now I go to this number basis function of the representation I rep 3 of dimension 1 contained 3 times in gamma, and I go with this representation now. So what I do is I copy it here and so this is the symmetry. Okay, so this is the file we are working now. So what I have to do is now I have to replaced this part in the PCR file by this part of block of the lines which was given to me after running Basirems. So copy it. I have pasted it here and file save. And now rest other things are the same which was there in the previous PCR file. You can see it here. The lattice constants are the same. Now, once you do it, it is always better to close this file and try to see in the edit PCR whether you can open this file. This gives you confidence that what you have done is all right as per the language of this code. So I see it here, everything is all right. Now I close it here and then see it from here. So here again, I would like to make the number of cycle, let's say only one, and I would make the number of refined parameter 0, and then try to see it that if I can get this magnetic intensity at the location where I need the magnetic intensity. So again, in this representation also, you have the three basis vector, which is given by n underscore base, 1, 2, 3. And when you go from this position of your magnetic atom to this position, this is how this moment should relate from the previous position. So now let's try to make this thing 0 and then try to see it, how it looks like. So the good part here now is I see this magnetic intensity almost at the location where I need it. Only what I can do is I can little bit try to increase it and see it whether still okay. So it is generating the intensity, but it is giving me some symbol. So now I have some hope that this representation might work. Then what I do that in that case is this lattice constant, as you know, were refined at room temperature. Then I will quickly like to do the refinement for this file and then try to see it whether there is some hope to get this magnetic structure corresponding to this representation. So I have done now. So I have entered in the refinement mode now by putting this code 1 here. 1 means it will try to refine this parameter C1 because I am working in this automation mode. So now you can see it is trying to generate some intensity. Of course, it is a little bit shifted. So we have to see it. So it means it is generating the intensity for the peak 0, 1, 0, but actual peak looks like to a slightly different location. Now, what we can do is we can play it with more, and instead of this coefficient, one coefficient, I can see it. What happens if I put this coefficient here? So let me save it. So this is not good. As you can see it is generating the intensity at different location. So this is how you make a progress in the refinement. So then I can put some value here. I can increase the number of cycles, let's say around 30. Then I can enter in refining these two parameters C1 and C2. Let us see how it looks like. So it's increasing C1, try to decrease the C2. You can play it little bit more. And now what we can do is we can try to refine once this ABC because they were refined at room temperature. So what I will do is I will try to refine first for the magnetic phase and then okay. So you can see this our lattice constant has been changed a bit. I can put for the nuclear phase and then I would like to refine them with the same code. Let me see how it looks like now. So you can little bit play with this, not much. And then you can play with this coefficient C1 and C2. And if you want to introduce, you can introduce this coefficient C3 here. Sorry. Now, when you introduce this coefficient, either you can calculate or you can see from the studio then what kind of magnetic structure it corresponds by giving this coefficient. So you can see. So this is the formalism how we keep this moment in terms of this basis vectors. Similarly, I have done this for the 2 and you can try to do this for the rest of the 2. Let me quickly do it for the number 3 also. What I can do is I can copy this. I have kept here this replica in this number 3. I go here and again what I have to do is I have to change this part of the PCR file. Now again let me try to refine this codes and see how it looks like now. Let me again check. I am in the okay. Again run it. So this is not good because it is generating this intensity at this location. So this is the way one should try for all this representation, and when your magnetic intensity matches, you can stop that point and you can see what is the magnetic structure and what are the values of moment at the sites by given by your refinement. So this is the way how you put the moment by this basis vectors. So in this case is simple. We have only 4 kind of representations are coming. So you can easily repeat this for one more and see what kind of result you get. Another way to write is this PCR file, the magnetic phases by these symmetry operations. So this also comes when you try to run this base reps file. So let me show you how it comes. So this is program base reps. Let me open the file which we did last time. This is the same file which I have run last time and let me run it again. So in the result there are 2 parts. One is the BSR file. Let us see in the BSR file. So this files gives you the information if you want to put the moment in another format. So these are the information here. So this gives the general expression of the Fourier coefficient Skj of atoms known related by lattice translations. And the Fourier coefficients are the linear combination of basis functions, and coefficient of this basis functions are u, v and w. So this u, v and w, and this is how it has come. So it is u time this, v time this, w time this for this side. Similarly, you can write it for this side, this side. So this is U, V, W, this is minus U, minus V, W for this position. For this position, this is U minus V minus W, U minus V minus W. Similarly, you can write for this side. And this is represented for all this representation. Now let's see how we go ahead with this formalism. Now what I do is I go to this another way by which you can add this magnetic phase. So this information now is in the terms of the symmetry operators and how this PCR file looks now. Try to make it here and let us see it. So first part here is still the same as previous. We have two phases. And now for this phase number 2, you can see it, what we are having is the ISY equal to -1. So what we'll give is this, we will give the symbols. Magnetic symmetry we will put in this PCR file like this. So when I writing ISY equal to -1, it means I will be putting magnetic symmetry instruction in the PCR file. Rest other thing I believe is the same. Now here in this case, what we are giving is the information about the moment in terms of their direct projection along this x, y and z axis, Rx, Ry and Rz. And this piece of this information, I am getting it again from this, you can see it here. So what it is telling is n sim is I have 4 symmetries, 1, 2, 3, 4, and these are Lovey class. And this value is how you write it, it is directly given in this PCR file here. This XYZ, UVW, minus X for this line, this is the corresponding line, and similarly for line number 3 and 4. Now here the advantage is that you can directly put this value of moment with respect to your crystallographic axis. And please note that when you are trying to refine this magnetic structure, you can keep your scale factor fixed once you have defined your data in the paramagnetic phase. Now let's try to run this file after putting this symmetry operation like this, which has been given in this base reps file. Let me again see it if I'm in this all right file. Okay, now what I do is I try to close this and let me run it. So looks like excellent. So we are getting very good agreement with this observed data. So this kind of fitting, if you tried in this basis vector information also, you can get it. So this is your choice how you want to work for this magnetic phase. Now again, if you want to play it, I can play it. What I would like to do is I can put a small moment and try to see it what it does. So let me see if I put the small moment what it does. So now what you can see clearly is that if I put this moment along this a-axis, it is trying to generate some intensity at some location where I do not have any magnetic intensity. So it means I should have no component of the moment along this a-axis for this refinement. This value of this temperature is wrong, and this issue is related with this comment line in the PCR file. This is 90K. I can save it and I can run it again. So file reset PRF Yes. So you see that keeping this moment along this A axis do not give us good fitting. I can try to see it by putting a refinement on this. You can see it becomes smaller, and in principle there is no intensity. So I believe what it is telling you is that your moments are along this B direction, and again what you can do it here is you can again go to this studio, open it, and you can see this magnetic structure or magnetic moment. So this is how we work for the magnetic structure determination. If you want to go for this other symmetry, then what I can do is I can copy this file, copy, paste, and let me put sim2. When I go again here, sim2, then I must change this operation. So what I do is to change this operation, I have to go in this symmetry calculation. Uh, Let me go to program, basic apps, open, symmetry, run, and result. So we have done the exercise with this, I believe. Now let's go to this extreme end. This, how it looks like. For this, what I have to do is I will have to change this, close this part. So this part I should change it. What I have is x, y, z is UVW minus x plus half. So what I can do is I can copy paste here. Copy and oh, where is my PCR file? I paste it here, and generally this is UVW, and this I put it as a second operation here. I put this corresponding codes UVW here. Similarly, this is the operation number 3, and these are the codes UVW and okay. So now I have copied paste all this information, so I can delete now this part. Rest everything remains again the same. And let me see now what happens with this representation. So I do it now, I save it, close it. Let me just open this file again and see it. Okay, so I close this now and I try to run it. So in this representation, if you see, the problem is, sorry, problem here now is with this representation, of course, you are getting the intensity for the first peak, but this kind of magnetic structure is also giving you some intensity for the second peak, which is shown here, where in principle you have hardly any magnetic intensity. So this indicates that previous magnetic structure was better than this. So this I have done for the second, and you can see how the magnetic structure looks now. Open. So it creates this two full Prof studio file. First one is generally for the structural, and second one is for the magnetic phase. So this is the another file. So this is how you can see how this magnetic moment are arranged and whether this observed intensity gives this satisfactory diffraction pattern as what you have observed in the experiment. So I have done it for this second representation. Similarly, you can go ahead and do it for this number 3 also, in which case I have to modify these lines and replace them what has been given by this base reps. So base reps again, you can open it. This was my symmetry analysis. I can run it just to make sure things are all right. And then we have worked for this, number 1, which was giving good fit. Number 2 was not good. Similarly, you can go ahead, this was number 2. Similarly, you can go ahead and try for this other representation and try to see whether you are getting magnetic intensity or not. This is how we work in the determination of the magnetic structure. So with this now, I would like to stop it here, and if you have some questions, you can tell me now. I think some of you have asked for this data file and the, I believe, PCR file, which now I will be sending, but I think it would be nice if all of who you need it can send the email so that I can. Okay, so I think it's a good suggestion. So I will try to give by today evening or tomorrow morning this data file on this Anuvidya portal. So from there you can download, and I will put this PCR file also, and probably this file for this base reps, which file is called SMB file. So the file which is opened in this base reps program has extension SMB, and what you can do is in future for your magnetic structure, you can only modify this file and then try to see this representation. And also they have not given assignment to me. So for your one, many of you have also not submitted the assignments for the theory of neutron scattering. You are requested to submit it as soon as possible. I would like to upload my assignment probably tomorrow, and then you can answer it. So now you can tell your questions, I think. Because these are very loaded. They're loaded, yes. I think I will prefer if you ask the questions, because that's how you can get this understanding about this subject. So maybe I will load the now file, and then you can practice it, and if you have doubt, then we can discuss them in this next lecture, which will be on Wednesday now. तो मैं आपको फाइल भेज